Yeah. All right, welcome to EE 123, Lecture 2. Woo! Good start. It's all going to be on YouTube. Last time I was a little bit reluctant to actually post on YouTube, because whatever you say, it's going to be documented forever. There's so many videos right now already because of the other class I was teaching. It's kind of buried in the noise. So hopefully nobody will hear this. Okay, so today we're going to talk about discrete time systems. Okay, this is so this week, well, whatever is left of this week, and next week is going to be kind of a review of previous material. We're going to cover discrete time systems today, DTFT, and Z transforms and DFT the next week. Okay, but it's going to be kind of like, and we'll be quickly pass by, and then we start moving on into other material. But the whole idea is that we're going to develop this language. Okay, language of notations, language of terminology, and this language is going to be used to create these tools. The tools to analyze signals and describe systems that are digital. Okay, so this is kind of the whole beginning of the class. We're going to develop the language, we're going to develop the notations, and then we're going to start using the tools. The tools are going to be certain transformations. Okay, for example, the DFT, DTFT, Z transforms, but also later you're going to see we're going to use the wavelet transform and so on and so forth. So you kind of see a series of things that will allow you to analyze and operate on signals. Okay, so last time I talked a little bit about administration, give you some overview of what the class is going to look like. I've got a few announcements. Homework 1 is out. Lab 0, bless you. Lab 0 is out. Webcast of the previous lecture is out. And next week, I'm out. Okay? But Julia is going to be in, and she's going to give the lectures. So be really super nice to Julia. Okay? Nicer than you are to me, and you're really nice so far, so that's great. Okay, so today, discrete time system. Any questions, by the way, administration-wise, anything before we go on? Quiet, are we? All right, I'll get it out of you. Okay, so what we decided we're going to do is we're going to do Cool Things DSP. We're going to try to present you with things that are DSP related, signal processing related, that are quite interesting. And so this is an interesting project that I came to notice. It's the ISEE3 Reboot project, and I really recommend looking at this. This is a 36-year-old spacecraft that was retired by NASA. And nobody has been communicated since '89, I think somewhere around that. And then it was getting closer to Earth, and so some enthusiasts, scientists as well as engineers decided, hey, NASA is willing to give us the ability to control the spaceship, although they kind of lost all the documentation of how to do this, kind of forgot. But then they dug into it and they actually found some documentation. And the idea that they came up was the project to go and take over this spacecraft and put it in orbit around Earth. Once you take control over it, you can use the thrusters and put it around Earth. And actually use SDRs and all sorts of things, these big antennas to be able to communicate and receive signals from it. Actually use GNU radio. One of the people that was involved there is Balint Sieber, and I hope to get him as a guest lecturer again this year. He gave a really nice lecture last year, and I hope to get him as well. He said he's willing to, so now it's on YouTube. Okay, so the aim was to take control and put it in orbit. The problem, once they actually were able to take control and everything, they wanted to fire the thrusters, and then there wasn't enough propellant. Okay, it was just disappear. So all the nitrogen that was supposed to be used to put it into orbit is actually dissolve over this 30-something years in space. So they used some of the data for analysis, but then the spaceship just kept on going. So it was, I would say, a partial success. but it's still quite exciting, I think, to see how scientists can actually take over and use, digital signal processing and signal processing and other communication to revive an old spaceship. Okay. All right. Are you ready? We're going to start. Quick. Discrete time signals. They're beautiful. Beautiful because you can count them. You can count them. You can store them on a computer. They're finite, both in length. Right? They can be an infinite sequence, but once you store them, there have to be some finite. They're countable. Okay? But they also have a finite representation because we're going to store them in a certain amount of bits. Okay? 32 bits, 64 bits, 120 bits, but it's going to be a finite representation. They could be samples of continuous time signal. For example, this particular one you're going to see quite a bit, and the question is, okay, if there are samples of continuous time signals, are they really representative of this continuous time? Are we losing information? Are we not losing information? What are the characteristics of that time signal and my sampling that I need to that needs to be in order to be able to save all the information or perhaps save important information? Okay. But it could be inherently discrete, and we talked a little bit about an example, for example, counting students that get into a classroom for every day. That will be inherently discrete. Okay. Now let's talk a little bit about some basic sequences. So again, developing a language that we're going to use. Very important one is the unit impulse. Okay, a delta function or a Dirac function, but a discrete Dirac function, as opposed to the continuous time where it's infinite at a certain point and 0 anywhere else. In discrete time, it is actually 1 at 0 and then 0 elsewhere. Okay, we can then talk about a unit step. And a unit step is, again, a discrete integral or a discrete cumulative sum of the unit impulse, which is 0 for negative values and 1 for all positive values of n. So there are some differences that you'll see between discrete time signals and continuous signals that are sometimes trivial, and sometimes they're not actually so trivial. Okay? So the treatments that we'll have to have is slightly different. Exponential sequences we're going to use to analyze, and you'll see that especially when we're talking about the Z transform. So an exponential is basically you have some constant multiplied by some alpha to the power of n, so it's an exponential series. And depending on what alpha is, that sequence is either going to be bounded or it's going to be unbounded. Okay? So when we're talking about exponentials, often we talk about one-sided exponential series. And then when alpha is between 0 and 1, you'll see that it's going to get bounded, it's going to drop to 0. Also, when it's between 1, it's just going to oscillate, but still going to drop to 0. But of course, if it's bigger than 1, it's going to go and explode. Okay, so there's some sequences that will explode, some sequences that are bounded. And we're going to analyze those, especially when we're talking about region of convergence, when we're talking about the Z transform. Okay, next week. So here's where things become a little bit interesting. So let's talk about discrete sinusoids. And by sinusoids, I don't mean sine function. A cosine is a very nice sinusoid, only 90-degree with a 90-degree phase shift, but also complex exponentials. Okay, we're going to also call them sinusoids. Okay. So a sinusoid has a frequency. This is the variable that changes, and it has a constant phase. So if this is pi over 2, right, then it becomes a sinusoid. Okay? If without this is a cosine, and so on and so forth. I can also look at the complex exponential. Everybody's seen this, right, before, right? Just calibrating. Okay. And now the question, we know that for continuous time, sinusoids, complex exponential, all of these are periodic. And so the question is that true for discrete time? could give you a hint. I probably wouldn't be asking you this. Right? So what do you think? What? Not always. Not always. Right. And it's really true. Yeah, it's not always. It's only if omega 0 over pi is a rational number. Okay? If it is a rational number, then at some point we're going to see the same value repeating over and over again. But if it's not, if it's an irrational number, that's never going to happen, and that sequence will never be periodic. Okay? It might be approximately periodic, but it will never be periodic by the definition that x of n plus n is equal to x of n. Okay? There's not going to be a period that you can actually define. Okay? And if you want to find the fundamental period for this case, then you need to find the smallest integers for which omega 0 times n equals to 2 pi k. This is basically multiple of pi's, 2 pi's, which gives you a period, and this needs to somehow reach that multiplicity. An example, if you have cosine of 5 over 7 pi n, for n equals 14, which gives you 2 pi's to go through, you would get a period. If you've got pi over 5n, that's n equals 10 for k equal 1. If you add both of them together, then the period is going to be basically for 70. Okay, so the smallest common multiplier. Okay? Any questions up to here? Okay, this is all relatively basic. Okay, and again, developing a language. What about which frequency is higher? Okay, it's pretty trivial. If I, for example, I'm going to annoy you for a second. Let's see. I have this app. Generates tones. You hear it? Which frequency is higher? The second. Which is higher? Right? I can't hear it. Can you hear it? Who can hear it? Raise your hand. I can't hear it. Who can hear it now? You can? You sure? Yeah, because 17 kilohertz, that's hard to hear. What about that? Who can hear it? Raise your hand. Are you less than 20? 21? No. Okay, so with age, it drops. Yeah, I can hear about 14.5 kilohertz. Yeah, at the sophomore class, like the lower division class that I taught, people were able to hear 18 kilohertz. Very young. But it drops pretty quickly from now on. So, okay, so it's pretty trivial though, right? Which frequency? That's actually the whole point, right? I wanted to see which frequency is higher, right? And it was pretty easy to see that in continuous time. What frequency is higher, right? So now I remember why I even started with this. But the question is that true for discrete time? And so let's pick, omega 0 equal pi or omega 0 equal 3 pi over 2. Which frequency, if you have cosine blah, 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 of that is higher? The second one, right? Because it's higher, right? All right. So let's draw this and see what happens, right? When omega 0 equals pi, then effectively, you change every pi. You end up seeing that is you get a 1, minus 1, 1, minus 1, and so on and so forth. When omega 0 equals 3 pi, you get this. So it's 1, and then it's going to go and do it's like 3/4 of a circle, and then 3/4 of a circle, and then 3/4 of a circle that you add on and on and on. So you get 1, 0, minus 1, 0, 1, so on and so forth. You count the period, and you see that the period in this case is n equal 2, The period in the other case is n equal 4. What happened? Aliasing. Interesting. So there's kind of the highest frequency kind of that we can represent in discrete time is actually pi. Okay, that's the highest frequency that we can represent. And it's 1 minus 1, 1 minus 1. Things that oscillate between plus and negative all the time. Remember that, just for intuition, it's the highest frequency that you can represent. Okay? If it doesn't do that, and it takes more than that to go into the negative and positive, negative, positive, then that means that it's a lower frequency. Okay? Either you get aliasing or you get, it's just a lower frequency by itself. And if you recall from 120, for those who've taken it, and I don't know about 20, but if you look at the DTFT, or discrete time Fourier transform, which we're going to cover next lecture, it has a period of pi. Right? It is periodic in pi, which means that pi is really the highest frequency, and you're going to see that next time. Okay, any questions? Okay. Just remember, highest frequency, discrete frequency, plus minus 1, the highest. Cannot go faster than this. I mean, can I change faster than within a sample? Like, what's high frequency? It's really rapid changes, right? That's kind of the definition of high frequencies, rapid changes. Can I change faster than going from 1 to minus 1 in a sample? Maybe in half a sample, but there's no such thing. Okay, so it's the highest possible change. Okay, so if you look at then on discrete sinusoids, this is stolen from the book. For omega equals 0, we get a constant. Okay, this is a constant sequence. This is pi over 8. Okay, so you can actually count the number of cycles that you get. This is pi over 4. This looks less like a sinusoid. This is pi, highest frequency. Doesn't look like a sinusoid at all, but it is. And so that's what happens with discrete time. Actually, if you look at sinusoids, they don't kind of look like sinusoids anymore. They're kind of different just because we sample them. But surprisingly, as long as they're below, if we sample it at a certain rate, then we'll be able to recover this sinusoid. So this sinusoid is still recoverable. Okay, we can recover it. Then if you continue on, and all I did now is reverse the arrow, kept the same figure, and starting adding numbers. Okay, we're going to go down. Okay, and we go down and down and down. We're increasing omega, but in fact, there's no faster than plus minus 1. So we start slowing down. And when we reach omega 0 equal to pi, we go back to be constant. Because there, it's exactly the same. I just skipped a full cycle. So the cosine changed, but when I measure it, it's going to be at exactly the end of the cycle. Okay? So that's why it is constant. Okay. Any questions? No questions. This is all clear. No problem. Moving on. All right, so now that we talked a little bit about sequences, we talked about some of the properties, let's talk about discrete time systems properties. So we've got a system, a discrete time system. We have an x of n, which is discrete time signal, going into that system, and something else comes out, some y of n. We want to look at what are those properties. One property, for example, is causality. Okay? Causality means that the output is going to depend only on previous inputs. There's no prediction. I do not know the future. Okay? Can you think of non-causal systems? Are there possible? Is it even possible to realize a non-causal system? I mean, our world is causal, right? Ooh, who said that? I like it. Who said space? Final frontier. That's right, space. Space, not causal. Right? Space. I can go that way, I can start here, right? It's not necessarily causal. When I put a needle of a what's it called, this thing that's rotating and makes music, and used to use it a long time ago, but then not so much, and now it's starting to come back? Vinyl record. Okay. I tend to forget words. So vinyl records, right? When you put it, you can go up and you put it anywhere, right? You don't have to start at a particular point, right? In a CD, it's not necessarily has to go through the entire CD, right? It's non-causal. You can start at some point. So you can actually do something that's not necessarily causal when we talk about space, and so on and so forth. Okay, so yes, there are definitely systems that are non-causal. I can give you another one that's non-causal. If I have a car that's driving on the road and there's signals coming out, right? But I also have a camera that sees where the car is going to be, right? I can predict what the signal is going to be, right? Just by another source of sensor, right? That I can predict what's going to happen in the future, right? And that's definitely non-causal in the sense that non-causal, we're going to, only when we get there, there's going to be that kind of an input, right? But we know we can predict something about that input, right? Just by using another sensor. Okay, very cool. Give me other properties. Go for it. Linearity, that's a good one. Very important one. You know what's important? Because most of the analysis that we do is about linear systems. And even the analysis that we do on nonlinear systems is by linearizing them. Okay? Linear is great. And often, it is so great that we can use it also for nonlinear systems. Okay? By making certain approximations that sometimes are valid, sometimes not so much. What else? Timing variance, very useful. What does it mean, timing variance?
Delaying the input is the same as delaying the output.
Pardon?
Delaying the input gives the same effect as delaying the output.
Right, delays in the input gives you differences in delay in the output. That's right. That's a very important property. Okay, because if we, for example, have a certain sensor, and let's say it's a temperature sensor, we'd like to see that if it's going to heat later in time, it's going to the sensor is going to show us the same heat, not like something else, right? Okay, so it's a very important property. Okay, so let's go through a few of them. Memoryless is it's a property where yn depend only on xn. An example for this is an example. Yn equals x square. Okay, this is a memoryless system. There's no storage. Okay, is it linear? Obviously not, because you have a square, right? Definitely not linear. Linearity has two properties: superposition and homogeneity. So it needs to be, the scaling of the input needs to give you a scaling of the output. If you add two signals together before you put it into the system, you will get the same thing as putting one signal, then the other signal, and then adding at the end. Okay, the outputs. That's basically what it means. It is very useful. Okay, and in a lot of cases, the systems that we deal with will have this property up to a point. Okay, up to a point. Here's an example. Let's say I shout into the microphone. Okay? Maybe it could reproduce my voice pretty well by amplifying it and then playing it. Okay? But how about two of us are going to shout into, you're going to shout to the microphone, it's going to maybe also be able to do this. If two of us shout, that might be a little bit too much. And we're going to go out of the linear regime of the amplifier, and the output is going to be distorted. Okay, so some systems will have linearity across a certain range, which is a good thing. We're going to treat it as linear, but in our back of our mind or head? What do you usually say? Mind? The back of my mind. The back of our minds. We'll think, okay, so we got to be careful not to overdrive the system into a point where it's nonlinear again. You'll see that with your software-defined radios I'm going to give you. Sometimes you'll be too close to a transmitter, you're going to overdrive the system, you're going to see lots of peaks in the spectrum, and it's like, whoa, how come there's so many peaks in the spectrum? It's just one peak in the spectrum that's driving it too much and creating nonlinearities, like creating effective interpretation of different harmonics that can occur. You're going to see that. You definitely see that when you speak into a microphone, and for example, you're going to get the radios, and the first thing you're going to do is shout into them, right? It's going to overdrive them, and you're going to get distorted signal at the end. Okay. All right. So linearity is very important. Sometimes things are approximately linear in that sense. Linear around a point, linear around a... Time invariance. We talked about it before. Delayed in the input gives you a delay in the output. That's very, very useful. Things can be, for example, approximately time invariant. For example, let's say I characterize, let's say I have a sensor that measures some signal, and over time, sensor is going to change temperatures, it's going to have a certain different response, but over a short period of time, it's approximately time invariant, right? But not over a longer time. Okay, so for real systems, you can have an approximate we approximate the system often as time invariant, but sometimes it's not really time invariant. And again, we have to put that into our mind. For example, again, your software-defined radios have an oscillator which it says on it 28 megahertz. Don't believe it. It's not really 28 megahertz. It varies. It has an oscillator that varies a little bit, and it actually varies up to 5 to 10 parts per million. So it can vary quite a bit. So you're going to get a frequency measure, and that's going to be approximately the frequency that you get, but then you hold it a little bit, and it heats up, and that thing will drift a little bit. But for a short amount of time, it's approximately time invariant. Okay, so you got to be aware of that. Bibostability is another very important property of discrete systems. And basically what it tells you is that if your system is bibostable, if you have an input that is bounded, the output is going to be bounded. Okay? And that's a great thing, right? That means that most normal type of signals that go in are not going to make that system go unstable and put an infinite value out. Okay? They're going to blow out. Okay? That's a very important feature. So if your input is bounded, the output is also bounded. Okay? Does it happen on all systems? Let's look. Okay, so let's look at this system. This system, y of n equals x of n minus nd. This is a shift, okay, time shift. Is this causal? Only if nd is greater than 0. Right? Then it's causal. Otherwise, you're shifting into the future. Then it's non-causal. Is it linear? Yes, it is, because it's easy to show that it scales, and if you add shifted values, then it adds nicely. Is it time invariant? Yes. If I shift it, I get a shifted output. Is it memoryless? Only if the output is exactly the input, then there's no need for storage. But otherwise, there has to be some storage, so it's not necessarily memoryless. And the question is stable? Bibostable? And yes, of course it is bibostable. What about the accumulator? Is it causal? Accumulator is kind of discrete approximation for an integral. Okay? If you think about it. Is it causal? Yes, right? Because we integrate something, right? Whatever's in the future, we haven't integrated yet. Great. What about linear? Yes, it is linear. An integral accumulator is generally linear. Well, you can actually show that. Is it time invariant? If I delay something, do I get a delay in the integration? And yes, actually. Is it memoryless? No, it's not memoryless, right? Because we have to remember what the values are, okay, as we integrate them. What about bibostable? No, it is not stable. Why? What if I put an input of ones? It's bounded. What happens at infinity? It's going to blow up, right? So it is not stable. All right. Compressor. Compressor is basically you sample the input you skip kind of time points and then compress them in time. Okay, so the output is kind of skipped measurements of the inputs. Is it causal? Is it? Why not? You have to look in the future because, eventually you have to skip, right? So you're skipping, you're putting samples the same rate out, but you're skipping samples of the in, so you got to, move to the future. That's right. Linear? Yes, it is linear, actually. Time invariant? Time invariant? Time invariant? No, it's not time invariant. Memoryless? No, because you have to save samples. And what about stable? Yes, right, because it's only the same samples at the input. Okay, great. Why is the compressor not time invariant? You said no, but it's kind of pretty obvious. Let's say you have this particular sequence. When we compress this one, basically we throw away every odd sample, so we get a sequence like this. We're going to look at the compressor later when we talk about, when we do multi-rate signal processing. So downsampling, upsampling operations, we're going to use compressor operations. So it's a very useful one. If we shifted by 1, what would happen? If I shifted by 1, then now I'm sampling the zeros. Obviously, we got a problem. It's not time invariant. Okay? So if I shifted, the output is not shifted. It's just dead. Okay? All right, so let's look at another example, a nonlinear system. Okay? Here's a really useful nonlinear system, which is the median filter. Okay? A median filter, do you know what a median filter is? Do you know what's a moving average? It's an average that moves. Okay? So if I have a signal, I compute the average over a certain finite set of samples. I move it, I compute the average. I move it, I compute the average. I move it, I compute the average over a set of finite samples. A median filter is the same, but different. Median instead of average. Okay. Moved, median, over a set of samples. Okay. So he takes a median. Here's the median over example with k equal 1. Okay, this is the input. This is the output. Okay, this is the input and this is the output. Ready? How do we test for linearity? What we're going to do is we're going to take this, compute the output, take another sequence, compute the output, add them both, and then compute the output. And if this is not the sum of this, then it's definitely not linear. Okay? Obviously, it's not linear. But here, just to show you, how do I compute a median filter? I take 3 measurements here, so that gives me the value over here. So 0, 0, 3 gives me median 0. Okay, so I got that 0 over here. And then I take 0, 3, 4. What's the median? 3. I get 3 here. 3, 4, 5, median? 4. I get 4. 4, 5, 0. 4, 5, 0. Then you kind of sort them. So 0, 4, 5. The median is 4. Yes. That's right, 4. And so you can compute the median here. You add them, you get this. You compute the median. You see that this is actually not the same as this. Obviously a nonlinear operation. Do we like nonlinearity? I love nonlinearity. While linear is nice in most cases, nonlinear stuff is awesome. It can do almost magic. Okay, and I'll show you this. Okay. Something that you would think is like, there's just no way I can deal with this. If I can do something nonlinear, you could actually do a lot of very, very interesting things. It's very hard to analyze them, but they're extremely powerful nonlinear operations. Okay. Is thresholding a linear operation? No. Extremely useful, right? If we want to detect something, right? Try to detect something without a threshold. I don't know. It's kind of hard. Right? Oh, it's a 2. So, is it above 1? Oh, okay. Great. That's a detection. That's an example. Here, let me give an example about... So one example I'm going to give you is removing shot noise. So listen to this.
There comes a time in life when we hear the greatest voicemail message of all time, and well, here it is. You dare to believe it.
Okay, so this is it was an episode in NPR, This American Life. I really recommend listening to this show. It's amazing. But there was this phone message. But let's say that what happened to it is actually, this is the corrupted message, and you really want to hear it, but this is what happens. You hear it? So it was corrupted with shot noise. What happens was this: either there's not very good connection, so you got lots of spikes in the data, or things are just completely overdriven. This happens quite a bit when you've got a lot of interference from, let's say, like even in radio, for example, if you have, let's say, power lines and they have lots of arc, they may have some arcing that's going on. That creates this kind of shot noise. And it's very, very hard to listen to, okay? So, I mean, what can we do in order to remove that shot noise? I mean, trivial thing, right? You compute, let's look at the spectrum of this, right? Let's look at the spectrum. So, spectrum of speech is somewhere between 2 kilohertz and 3.5 kilohertz speech. Corrupted, the one with shot noise is, just impulses. Impulses everywhere, has lots of frequencies. Okay, so the spectrum of shot noise spreads out almost everywhere, right? So we could reduce the shot noise by filtering a lot of it out, right? And that will be a linear operation just by kind of bandpass or low-pass filtering, right? So after we do this is an example, right? So we filter. Let's try to hear. It's kind of difficult, right? Not very good quality, right? The problem with shot noise is, it spreads everywhere, but it really spreads also on your particular signal, right? So it's a significant amount of noise that's going on. Low-pass filtering reduced it, but didn't eliminate it, okay? Let's look at the time signal and see what happens and see what the corruptions are, okay? And here's why it was not that effective. This is the shot noise. Shot noise basically gives you maximum positive or negative kind of signal, right? This is the original signal, right? You can almost imagine it. Can you imagine it? Like how it would continue, right? But it is corrupted with these spikes in the data. When we filter this using this linear operation, those spikes create huge bias on that estimation, right? Because we're kind of doing a linear operation. What is a filter? It's a weighted kind of sum of nearby samples, right? It's some weighted sum of nearby samples. The spikes are just always going to bias this. And so we get a distorted signal that doesn't look like the original one. Any ideas? Median filter. That's actually a pretty good idea. Pretty good idea. There's other ideas. Anybody has other ideas rather than a median filter? A what? What's a min filter? Oh, just the minimum. You first take the min and then take the max? You might actually keep quite a bit of the spikes if you take the min. Right? And then you end up with a max. Right? So that. Anywhere else? Anyone else? Oh, threshold. So you do kind of a moving threshold and then see, oh, there's a spike here, and then I need some way to estimate what's in between. Then maybe I can do then I could do a filter, like a linear filter, right? But then it's definitely nonlinear because I need to figure out a threshold and then do different filters for different parts, right? So that's an adaptive kind of a filter, okay? But definitely I can do something else than just using something linear, right? If I do that, if I do a median filter, look, it's just beautiful. You know, it almost it recovers this so beautifully. It gets rid of all the noise. It's really good at removing also what's called a salt and pepper type of corruption in images, for example, which is black and white type of pixels, white pixels. Actually, all your cameras have white pixels on the sensors. A lot of way to deal with white pixels is some median filtering or some sort of type of operations in cameras as well that do exactly this. So let's hear what happens after you do this filtering. Okay?
So you get a kick out of this message from my father. I said you and the Little Mermaid can go yourself. I told you to stay near the phone. I can't find those books. You have other books here. It must be in La Jolla. Call me back. And I'm going to stay up all night for you. Goodbye.
You should listen to the whole show. There's a whole story about it. Okay. Anyway, that's a funny one. All right, let's move on. Any questions, by the way? Any questions up to here? So nonlinear operation, so powerful, so powerful. Look, just a simple operation, just a median filter. No, like sophisticated, trying to figure out a spectrum, blah, 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 blah. No, just a median filter, done. Removed everything, almost perfect reconstruction. That's incredible, right? What is the statistics of the noise after that? Kind of hard to then estimate, right? So there's advantages and also disadvantages. Okay, let's look at discrete. So now we can look at discrete time LTI systems. So we looked at discrete time systems, but now let's look at a class of system which is discrete time LTI system. Nice thing about LTI systems is that they are completely characterized by what's called an impulse response, okay? Which is kind of like the DNA of those type of systems. Yes, thank you. I have to catch a flight, so I'm getting all this. Sorry. All right, so that's why I won't be able to stay actually after class. Run. Okay, so what is an impulse response? It's basically what it is. You put an impulse, a discrete impulse, right, a unit impulse, into the system, and you watch what happens. What happens is H of n. You save it, DNA. The good thing about it, completely characterize the system if it's LTI. Now, put any input whatsoever. What's the output? I don't need to know the system. Give me an input. No problem. I'll take the input, I'll convolve with the impulse response, and I'll give you the output. I don't need even to measure what the output is. I'm going to tell you what it is. Extremely, extremely powerful. Extremely powerful. Basically, for LTI systems, if you give me what the impulse response is, the output is just going to be a weighted sum of delayed impulse responses. Okay, whatever the input is, I'm just going to, attach an impulse response to it and add it to the rest. Another sample comes in, I'm going to attach an impulse response and I'm going to add it, and so on and so forth. And add them all together, and that's going to be the output. Okay? Extremely, extremely powerful. Let me give you an example. First of all, what's an impulse response? All right. Definitely an impulse. And this is the response. Look at this. It's beautiful. Oh, you see that? Beautiful impulse response. Now, let's say this room was an LTI system, which is it? Let's say you didn't move. Everything was stagnating. Temperature was not changing. Yes. If I would hit exactly the same spot, right, it would be an LTI system. Okay? And then all I need to do is measure this, and I can dance, and I can tell you exactly what the output is going to be at this point of the microphone. Okay? Not anywhere else, but at this point. Okay? And actually, what's cool about it is that if you want to characterize a room, you put a lot of microphones. You create different inputs. Then you can characterize actually how room propagates sound. Then you can create this amazing effects, like 3D effects or focus sound into a particular point if you have lots of microphones and so on and so forth. But that's another story. Very powerful. I can just now dance, and I can predict, just by looking at the impulse response, what's the output is going to be. Okay? Questions? And if it's discrete, I can just do it on a computer. Extremely, extremely useful. If I want to design a particular output, why would you like to do this? For example, if I want to design a particular output, okay? I know that you have a system with particular impulse response. I can design maybe the output such that I can design an input such that the output is going to be actually what I want it to happen. Okay? So I can correct, for example, for certain aberrations. Maybe. Okay? I can correct as much as I can. Sometimes you cannot correct fully, but it is possible. So it's very, very powerful. All right, in the last 2 slides, I want to talk about bibostability. Bibostability is an LTI system which is stable if and only if h of n is absolutely summable. This is a criteria for bibostability. If you look at the impulse response for LTI systems, and the impulse response is absolutely summable, that means that the system is going to be bibostable. Very useful. Give me an LTI system, give me the impulse response, yeah, it's stable. Give me the impulse response, it's not stable. You know, I can tell you just by looking at the impulse response if this is a stable system. Okay? Very, very useful thing. How do you prove it? Well, you have to prove it both ways. Okay? You have to prove the if part. Okay? So if h of n is absolutely summable, you need to show that the output is going to be stable. Okay, let's do this. It's actually relatively trivial. So we're going to look at the output and see if the output is stable. So we're going to look at the absolute value of the output. Okay? The absolute value of the output is the convolution between any input and the impulse response. Okay? So this is exactly y of n, because I can characterize it. Take the absolute value of this. But of course, this is less than the absolute value of this multiplied by the absolute value of this. Right? Great. But I know that this is bounded. Right? Because I have a bounded input. So this is less than some b. Okay? So then the whole thing is less than some b times the sum, absolute sum, of the impulse response. If this is bounded, then everything is bounded. Okay? Now we need to show the other way. The other way is less trivial. The other way basically says the following. So the only if is suppose that the impulse response is not absolutely summable. It actually goes to infinity. We need to show that there exists some bounded x of n that still gives an unbounded y. Okay? if h of n is not absolutely summable, we need to show that there is some bounded input that will give you a non-bounded output. Okay? And so what we're going to pick is we just need to pick one. And the one that we're going to pick is interesting. We're going to pick the sign, okay, signum of the impulse response. Okay? The signum of the impulse response. Why is that? Because what I want to create, effectively, if I know that the impulse response is not absolutely summable, okay, I want to create some sequence that would absolutely sum it at some point. If I'd absolutely sum it at some point, it's going to go to infinity. Right? Signum is a function that gives you the sign. If I multiply something with its sign, it's always going to be positive. It's going to like taking the absolute value. Signum is also bounded. Okay? So if, for example, I have a sinc function, okay, as the impulse response. Now I'm going to have x of n be the input to be the sign, the signum of the sinc. So at some point when I convolve them, they're going to exactly align. Now the output is just going to be the sum of absolute value of that sinc. What is the sum of absolute value of a sinc? Infinite. Sinc decays like 1 over x. It is infinite. Okay? So that gives me a sequence for which at some point when exactly those align, those two sequences align, I get the sum of absolute value. And because I know that this is infinite, then I get, for a bounded input, I will get an infinite output. Okay? If you have more questions about this, office hours next week. But I will have to end today. Have a nice weekend. I will see you only the week after. Be nice to Julia. Okay? Homework 1, lab 0 due in 2 weeks. Homework 1 due in 1 week. Okay?